Okay, let's jump right in here and draw our lines for your Cornell notes. Go ahead and write the date. Okay, up in the top left corner. The date that I'm making these notes right now is November 28th, but it might be a different day for you. And our essential question we're going to use here in green. What are the differences between vector and scalar quantities? Okay, and if we come back over here, we are in explore number 1. It's called using vectors and scalars to describe motion.
Yeah.
Okay, you can take a look here and see we've already done Newton's laws. We've already done understanding and describing motion, so we're on the 3rd chapter of 5. Okay.
So the password
and
is EDW. So
if
the
we come in
username
here,
is slowmeyer@gmail.com.
you can see that the name of this
and
unit is forces and motion.
It's securecafe.com, right?
And here we are on 1.3.
Yeah, here's
concept 1.3. All right, so that just is to help orientate you guys, okay?
So I'm going to send you a picture.
So let's start
that's what I'm getting into.
This by saying what you already know, okay? What I know or what you think.
Okay, so I just
Okay. And make sure you just take a moment, think about vectors, think about scalars. What do you know about these ideas? Okay. So as I take a look through the text here, I can see using vectors and scalars to predict locations. Where are we at? We're actually on the engage page. Let me get back over here to, the explore page. We can see our essential question, and they're going to talk about 2 things, scalar quantities. And it looks like we've got some vocabulary words there, and they're going to define it for us, and they're going to provide us with some examples. They've got a video segment, and this might be worth noting here, calculation of speed. Okay, it looks like there's going to be some formulas they're going to provide for you. Okay. And then they're going to talk about vector quantities. It looks like they'll define that. There'll be some vocabulary words associated with that. And they're going to provide some examples. Okay. Then they kind of go into the way that you communicate vectors. And we'll talk about that in our notes. And they also talk about being able to mathematically add and subtract vectors, when you can do that and when you cannot. Right, and we got some homework problems there as well. Okay, so that gives us the lay of the land. Let's go ahead and talk about scalar quantities first, okay? If you've already watched the videos, you may recall that they've talked about both scalar and vector quantities as being mathematical representations. Okay. If we look at this definition here in yellow, a scalar quantity is a value or measurement that has magnitude or size only. Okay. It's a value or measurement that has magnitude or size only. Okay. So it's going to have units, but does not include information about direction. Okay. So it has units, but not directionality. Gives us no information on direction. Okay. Now, if you take a look at some of the examples they provide you here, mass is a scalar quantity. We could say that the bowling ball has a mass of 10 kilograms or 2 kilograms or whatever. Doesn't tell us anything about direction. That just tells us the mass of the object. Distance, 12 miles. It is purely a quantity, right? It's a numerical number, does not tell you anything about direction. And you can kind of go down this whole list and see that some of these things are familiar to you. And the point is, no direction is communicated. Okay, these are all just quantities by themselves. Okay. Maybe we can give it over here, i.e. examples. We could say mass. We could say that distance, length, okay, etc. Okay, we're not going to rewrite the whole list or anything, but that just kind of gives us a little bit of a sense there. Okay. Scalar quantities are expressed with a number and the relevant units. Okay. So if we're talking units, if we were talking mass, we would say kilograms. If we were talking distance, we might be talking meters. And if we were talking length, we could also be talking meters, right? Okay, so those are just to kind of give you an example of that, okay? Okay. Make sure you watch that calculation of speed video, okay? And now let's move on to vector quantities, okay? That was pretty easy. Okay, the definition here. These quantities have magnitude and they have direction, okay? They have both magnitude remember we said magnitude or size and they also provide information on direction. Okay. Physicists use the vector term velocity more often than they use the scalar term speed. We've already talked about this, right? Speed is just, how fast something is moving, and a vector is to say that you're not only going 80 miles per hour, but you're going 80 miles per hour north or south, right? So we could say example is speed, which is scalar, versus velocity, which was a vector quantity. So the speed would be to say something like you're going 80 miles per hour. We should probably say, since we're talking metric system, maybe we're saying you're going 80 kilometers per hour, and versus saying 80 kilometers per hour northbound. That means you're traveling north, right? Velocity would be this one. It's a vector. And the speed, scalar, would be this term with no direction. Okay. All right. Review, right? So consider some of these other examples of vector quantities. Displacement. Maybe you could talk about a location. I was displaced 2 meters from where I was standing. I was displaced 2 meters east, right? There's that directionality. Not only talking about a distance, but you also describe the direction. Accelerating. I was accelerating 20 meters per second squared, straight up, vertically, right? So these are ideas. These are examples of vector quantities, but they have to include the directions. Okay. Sometimes vectors are indicated in text. This is probably important. Bold-faced or in italics, and they often are written with an arrow on the top. Okay. The direction and the units are included. Okay, so this whole statement was a good statement. Okay, and as we take a look here, we can see there's the vector, right? That's interesting. There's the arrow, right? We've got the units, and we also have the direction. Okay, so, and we want to write that down too. Okay, often written in bold or italics. Okay, type, right? Bold or italic type, often written with an arrow Okay. Often written with units and direction. Okay. And so they had some examples there where they said velocity was equal to, and you may say 80 meters per second west or east, right? You could have said that your force, you could have said your acceleration, okay, all of these, and your velocity, right? And you used the arrow in there, okay? It is often useful to draw vectors as part of a diagram of an object that is moving or that is subject to forces. So we've seen vectors in diagrams. We've drawn them as maybe a force is pushing a box with 4 newtons of force. This is a vector quantity, right? The arrow points in direction, right? And the size of arrow communicates magnitude. So I could say, for example, that this was a small arrow, and this one has only 2 newtons. So notice how one arrow is short, one arrow is longer. Shorter arrow, right? So this is just kind of making sure you understand what they're talking about here, okay? That's to say that the length of the arrow indicates the magnitudes, and the direction of the arrow shows the direction of the vector, okay? You may draw it in a different way. We may say that you got a person who is shooting a bow and arrow. Maybe they got a bow, right? And they're going to pull back their arm, and they've got an arrow. Right? No. And they shoot the arrow, and you may say that they shot the arrow and you could say, if you were to draw lines, you may say that the arrow is displaced so far on the x-axis and so far on the y-axis. You could say that it went up to, this height, and you may say that it went this far on the x-axis, right? So you can kind of use these vector quantities to show motion, right? You could say that that arrow had had both an upwards quantity aspect to it, and it had a horizontal quantity to it, if you want to break it down into different parts there, okay? There is an upwards component, and there was an x component to it as well, okay? And again, this is just saying that these things can be used in diagrams, right? And they can be two-dimensional like we just drew, or they can be three-dimensional as this picture is showing. And let's also make a point here. Two or more vectors of the same type can be combined. That's the key, an important part. Of the same type can be combined. How do we want to do this here? Combining vectors. This is allowed if we're talking the same units, right? That's the important part. If the same type, the same units, okay? Add if they're pointing in the same direction. Add if vectors point in the same direction. Subtract if vectors point in opposite direction, okay? So, and you know this already. If I were to say that I had a box and I said that somebody was pulling with 1 Newton and somebody was pushing with 2 Newtons, then I could say that combined 2 Newtons plus 1 Newton equals 3 Newtons of force. And I could say to the right. Now, if I had versus, if I have this situation where I have, we'll say 1 Newton, but this time I have 2 Newtons to the left. These are in opposite directions, so I have to subtract them. I have a positive 1 Newton plus a negative 2 Newtons because it's going to the left. And the difference, the net force, is a negative 1 Newtons left, right? To the left. Okay, and notice how this is basically a subtraction problem. When you add their opposite signs, you're basically subtracting. Okay. All right. Make a note. You cannot add different types of vectors. You can't add a vector for direction, for velocity, with a vector on displacement. Okay, they got to be kind of the same terms. Okay, and vector quantities cannot be added. And let's just put this over here. That's probably good here. Can't add vectors to scalars. Okay, can't do that. All right. All right. Is that all we have here? Could be. Got an example problem. And that was it. All right, so that was nice. We like these when they're short.